Welcome back. In this lesson, we're going to begin our study of earthquakes with the forces that would cause an earthquake and how that the ground then behaves as these forces are in play. So what is causing the ripples, what is causing the movement of the earth, and how do rocks essentially react to being put under such force and stresses and strains. So let's look at some examples. So earthquakes are caused by huge patches of ground that is moving in some way relative to each other. So they're either moving into each other, or moving away from each other, or sliding across each other. And the ground is not perfectly smooth, so it's going to grab, as it's moving, it's going to grab each other. So imagine like two pieces of Velcro that's hanging on together, and you're pulling one in one direction and the other in another direction. You may pull a long time before it actually breaks, but if you pull hard enough, it will break. It will grab and then break. And sometimes, instead of just a nice smooth movement, it will hold, pow. And all of that energy is released at once, and that is what an earthquake is. So this force that is put on these rocks can build up in such a way to cause resistance. So stress, is a force acting on a rock. So it's a force making a rock want to move, but the rock is somehow stuck to another rock. It has either microscopic bumps that is holding it, or larger than microscopic, huge big things that are holding it, and the forces that would be caused, that forces required to cause one huge piece of land to move in one direction and another piece in another direction, are ridiculously big. So the stress, you can put stress on it in some different ways. You can either compress. You can compress two things together. So you can squish them together. You can kind of push them up in the middle. That's compression. Tension, you can either pull them apart. So imagine compressing Play-Doh, and you get a kind of a pile in the middle as it bumps in. Or tension, you're pulling it apart, and you end up with a dip where all that material has pulled apart from each other. That's called tension. And you could have tension within stresses within the earth that would either be compressive, which pokes them together and forces them in on each other, or tensional as they pull apart. Shearing stresses are what we think of more in terms of earthquakes, where you have a fault line moving in opposite directions. This is what would cause very dramatic earthquakes. So a different type of stress is, or when a material deforms because of stress, that's probably a better way of saying it, is called strain. All right, so if you have a material that reacts to stress by changing its shape, then that is called strain. So the strain everybody's familiar with would be if you were to squeeze a ball and it pops back out, then that ball is somehow elastic. You have an elastic quality to it, and that's called deformation. So it compresses it will bend, and then it usually disappears. It'll come back or restore to its normal shape. That would be elastic deformation. Plastic deformation. Now, plastic not as plastic as a stuff, but if something is plastic, it can take a new shape. So imagine taking some clay and putting your finger in the clay, and the clay now holds the shape of your finger, the print of your finger. That's plastic, because it doesn't restore to its original shape. It now has a new shape that you just forced it into. That's plastic deformation. A lot of times, how warm a material is will have something to do with that. So, like warm wet clay would be more plastic than, say, dry baked clay. That would be less likely to hold your fingerprint, for instance. Now, with these strains, you can get all kinds of cool shapes. You can fold And remember, a lot of this is done when you had metamorphic rock. You're going to get these shapes in them. So folding, buckling like that, stretching out to where it's thin in one area and thick in another. And then shearing, where one's going kind of in one direction and another's going in another direction. So you get kind of horizontal, wavy lines as you're looking down on a rock. That's shearing stress. And a fault is when it cracks. So if you have a fracture in a huge portion of rock, then that is called a fault. All right, so the surface that the two big parts of rock are going to move along is the fault. Okay, so if you were to have something like this is called a normal fault. So a normal fault is when one drops down and leaving the other one higher, because the other one higher is called a hanging wall. All right, so the hanging wall is moved downward. The one that's up is called the foot wall, because it's what you're looking at. So the hanging wall is dropping, and it leaves one there. Now it looks like the one's raising up, but really what happened is the one is lowering. So if the crack is at some kind of an angle and one drops and one raises, then what's dropping, that's called a normal fault. Okay. Reverse, obviously, is the other way. Instead of the hanging wall dropping down, a reverse is a shortening. So it's usually really steep, a greater than 45-degree angle, so close to straight up and down. Okay, but a reverse fault, instead of the hanging wall falling, it essentially becomes the foot wall. So the one drops down below and the other one rises up above. You're going to get a distinctive, rather than a cliff, you're going to get a distinctive kind of hanging cliff, like a strange kind of hanging jutty place. All right, a strike slip fault is the third. Okay, so this is horizontal shear. So that means one is going in one direction and another is going in another direction, and the movement is horizontal rather than up and down. Okay, so if you have strike slip, this is normally what we think of as like a California earthquake, where you have one fault, you have a fault and one area going in one direction and the other going in another direction. Usually it's because you have a plate on both sides of that fault line. Okay, you have one plate and another plate, and one plate's moving in one direction and the other one is moving in another direction. Now, when you have this movement, it is going to reverberate with the rocks, because it's building up stress, and then boing. That's exactly what happens. One goes in one direction, the other goes in the other direction, and all of those rocks are bending back and forth just like a guitar string, and it's making sound. It's making waves in the rock. So just like sound waves are waves in the air, you can have earthquake waves, which are these vibrations inside the solid material. Okay, so the first type, there's two main types. The first type is called body waves, and this is primary waves. So they're called P waves. Okay, and they are going to go in a horizontal way. So essentially, they propagate in one area. So there's a motion in one direction. So there's a squeezing and a pushing. Okay, so it's going back and forth and back and forth and back and forth. It's pulling apart, squeezing together. So you end up with a kind of a compression wave. This is very similar to how sound works through the air. It is a compression wave like this. Your secondary waves, they're called S waves, and they're not called S waves because they're secondary. That drives me nuts. They're called S waves because they're slower. P waves are called P because they're primary. Okay, they're primary. They're the first ones that will get somewhere is the primary waves. The S waves are felt second. So if you have waves from an earthquake, you'll feel the primary waves first and then the secondary waves second. Okay, these are perpendicular to the direction of the waves. All right, so this is kind of a back and forth. So this is a rolling motion. Rather than simply the ground pushing into the ground, the ground is actually going to rise and fall like the water waves. And so these are secondary. Now this is slower to get somewhere. So if you are measuring an earthquake somewhere away from the epicenter, then you will feel the S wave second, because it takes longer for this ground to go up and down and ripple as long as from wherever the original spot is to wherever it's being measured. Okay. And then the last one are called surface waves, and there's two types of surface waves. There's R surface waves and L surface waves. All right. The R surface waves are called Rayleigh waves. They are slow, and they only travel on the surface. So they don't travel deep. This is not a vibration that's happening deep, but this is like a rolling. So in a lot of ways, this is very similar to water waves, because water waves don't just go up and down. They're rolling in circles, and so you get kind of very shapely curves. I don't know. I'll just show you the propagation. Okay, so you're going to get curves that are stretchy in the middle and then compressed along the side. So these are not just up and down, but these are elliptical. Okay, an elliptical surface wave. These are called Rayleigh waves. They're pretty cool. Boy, I'd hate to try to describe that with a piece of chalk. And then the last one are called L waves. Another scientist named Love. I don't know why his name was Love, but his name was Love. And they travel on the surface, and they're horizontal. So this is a transverse wave, similar to the wave like a guitar string would generate. So one's going in one direction, the other's going in another direction. So essentially, it's up and to the side at the same time. Okay, it's going up. They're surface waves. They travel on the surface. They have a horizontal motion, so they're wiggling back and forth, and there is an up and down motion at the same time. So there's a transverse and perpendicular, so it's rising above the normal surface. Okay, so like a building would actually rise and then fall, and it's going left and right at the same time. So it's love waves are very complicated. I would hate to do the math. All right. So the generation has to do with where the Velcro was. So if you're moving one in one direction and the other direction, and they're holding, and then boing, the boing is the place where they were grabbing each other is the focus. And that is very deep usually, because it's rocks grinding against rocks. So where are the rocks holding onto each other? That's the focal point. And the focal point is low in the ground normally, almost never on the ground. The epicenter is the point on the surface of the ground that's directly above the focus. So the epicenter would be on a map where the earthquake was, but the focus would be on a 3D map of how deep this was. Okay. All right.